Welcome back to differential equations. In this video, we're going to wrap up our discussion of the method of characteristics. We've seen that we can use the method of characteristics to solve a second or higher order linear homogeneous ordinary differential equation with constant coefficients. Doing so gives us a quadratic equation, and that quadratic equation can have two real roots, in which case the solution is going to involve exponential functions. It can have two complex roots, which are either completely imaginary, in which case we have sines and cosines, or complex with real and imaginary parts, in which case we have exponentials and sine or cosine. The case we haven't looked at yet is the case of the repeated root, where we only have one solution to our quadratic equation. With only one solution, we don't have two linearly independent solutions that we need to write the general solution of the differential equation, so we need to do some more work. Once again, this is one of those places where if you are interested in a constructivist approach, there absolutely is one. Our textbook goes through it, and it would take about a video or two just to go through that. I don't think that there's a lot we gain from doing that. I don't think it adds a lot to the conversation. So instead, I'm going to take this from the reductionist standpoint. Most of what we're going to be talking about in this course, most of the theory of differential equations was created kind of from the top down. It's not a unifying theory of here is how things come out. It has long been, I don't know, we need something to work. Let's start poking at things and hope that we can find something that works out. And eventually somebody finds something that works nicely, writes it down, and then the mathematical community gets behind that and tries to figure out why it works. And we call that why it works the theory of differential equations. So rather than trying to present this from the bottom up, I'm going to start at the top down. Let me get my head out of the way. That's not enough. All right, so let's assume that the differential equation a times y double prime plus b times y prime plus c times y equals 0 has a repeated root c for its characteristic equation. Well, from that assumption, we know a couple of things. We know that y1 of t equals e to the c times t is a solution to the differential equation. And we know the characteristic equation. A times c squared plus b times c, that's not a c, that's mostly a c, plus c equals 0, has exactly one solution, and it is c. My claim is that a second function generated as t times e to the ct is also a solution to this differential equation. Right? And again, that's not obvious. where this came from is not obvious. I could spend an hour or so going through and showing you where it came from, but I don't think it's interesting. I can shortcut about half of that and look at it from the other direction. Instead of showing you how this came to be, let's at least prove that it works. Let's take the derivatives of this function, plug it back into the differential equation, use the fact that the characteristic equation has this repeated root, and show that the solution actually does work out. All right, well, y2 prime of t, product of two functions. So take the derivative of the first function, derivative of t is 1, multiplied by the second function, e to the ct, plus take the first function t and multiply by the derivative of the second. The derivative of e to the ct is c times e to the ct. And if I factor out the e to the ct, I get 1 plus ct e to the ct. All right, that's easy enough. Let's take a second derivative. All right, derivative of the first times the second. The derivative of 1 plus ct is c times e to the ct. And then we'll have 1 plus ct times the derivative of e to the ct, which is c times e to the ct. This will take a little bit more working out, but multiply everything out. Combine some like terms. And factor out the exponential, and we get 2 times squiggle plus squiggle squared times t, e to the squiggle t. And then I want to take those things and substitute them into my differential equation. So my differential equation is a times y2 double prime, which is 2 times squiggle plus squiggle squared times t times e to the squiggle t, plus b times y prime, which is still at the top of the screen, 1 plus squiggle t e to the squiggle t, plus c times y, which was t e to the squiggle t. And that should be equal to 0. From here, I'm going to use a similar process to things that I have done before. I'm going to factor out the common factor of e to the ct. And using the zero product rule, one of these two factors has to be 0, and exponential functions can never be 0. So we are left with a times 2c plus c squared t plus b times 1 plus ct plus ct equals 0. Now I'm going to do some more arranging. multiply through to get rid of the parentheses, and then regroup things. Get all of the terms that have t together in one place and all of the terms that do not have t together in another place. So we've got 2a squiggle plus squiggle squared a t plus b plus squiggle bt plus ct. And if I take all of my terms that do not have a t in it, that's 2a times c plus b. And if I take all of my terms that do have a t in it, and I factor the t out, that's a times squiggle squared plus b times squiggle plus c. And look at what we have here. This second grouping, that literally is the characteristic equation. We know that C satisfies that characteristic equation, and so this has to be equal to 0. That whole second term just goes away. Because if I scroll all the way back up to when I was writing down things I know in yellow, I wrote down that that was equal to 0. And so I'm left with 2a squiggle plus b equals 0. Which I can quickly solve and get that c is negative b over 2a. And hopefully for some of you, as soon as you see that, a connection starts to flare up in your mind. Because remember that when we solve the characteristic equation, we use the quadratic formula. C equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And the case of the repeated root is the case where the stuff inside the square root here is equal to 0. Right? That's what it means to have a repeated root. And when you make that stuff become 0, you get that c is negative b over 2a, which is exactly what we just came up with. All right, so that verifies that we have here two solutions, or this y2 that we invented is in fact a new solution to the differential equation. Once again, this is something that I suggest just putting in your back pocket. This is a tool that you know will work. When you have repeated roots, you get your exponential function that you expect, and then you create a new one by multiplying times t, or by x, or whatever your independent variable happens to be. All right, let's take a look at what that does in practice. All right, so here we have a second order linear homogeneous ordinary differential equation with constant coefficients. Y double prime plus 6y prime plus 9y equals 0. And we don't see anything particularly strange about this at first glance, so we try to solve it using the method of characteristics. We get c squared plus 6c plus 9 equals 0. And we try to factor. We look for things that multiply together to give us 9 and add together to give us 6, like 3 and 3. So this factors into c plus 3 times c plus 3 equals 0, which means that we have solution c equals negative 3 or c equals negative 3. That's the same solution twice. we are left with repeated roots. Well, we know what to do now when we have repeated roots. We're going to have some constant C1 times e to the c, which in this case is -3 times t, plus some other constant C2 times the new thing we just realized works, t times e to the -3t. And whenever you have the repeated roots case, you know that that's what your solution is going to look like. All right. Rounding out the set, let's again end with an initial value problem for you to try. I've got 4y double prime plus 12y prime plus 9y equals 0, which is a second order linear homogeneous ordinary differential equation with constant coefficients. There's nothing to say that this is going to have repeated roots, but based on the video, you probably can make a good guess. And then we're going to have our initial conditions. Y of 0 is 0, y prime of 0 is 1 in this particular case. All right, take a few minutes, see what you can do with that, and I'll see you in the next video.